So in the last video, we talked about how the uneven distribution of heat on the Earth's surface causes these global scale wind patterns that fundamentally redistribute warm air from the equatorial regions to the poles. One of the things we mentioned was that near the equator, so here's 0 degrees, here's the equator, we've got warm air that rises here and moves to the north and to the south. And when that air cools off, loses all of its moisture, and sinks back down to the surface at about 30 degrees north and south, we have these very arid areas. So the classic example of this is North Africa right here, sitting at about 30 degrees north. Of course, the Middle East and parts of Central Asia, all major deserts in this sort of 30 degrees north area. Also, we've got the sort of desert southwest of the United States and parts of Mexico sitting right around that same latitude. And then if we come into the southern hemisphere, the Atacama Desert in the Andes, very arid. South Africa is very arid, and of course Australia all sit in this sort of 30 degrees south area where we expect our deserts to form. And then the equator, sort of exemplified by the two biggest rainforests in the world, right? We get the Amazonian rainforest here, and then sort of the Central African Congo rainforest here, right over the equator. Very, very wet, very damp places. Same as sort of Indonesia, Southeast Asia area over here. So that's the sort of, consequence of this global scale wind pattern that's developed because of the uneven distribution of heat on the Earth. But you might be asking yourself, is this weather or is this climate? And how do we know the difference between the two? So this video, I want to just clear up a little bit more about the differences between weather and climate with that context. So we know from the last video that these things called Hadley cells sort of form these predictable wind patterns in the mid-latitudes, where wind is sort of blowing in this direction in the northern hemisphere, and then similar pattern in the southern hemisphere with prevailing winds like this. Okay, so this is a sort of global average of wind direction, but it's complicated. So it's most obviously seen, like you saw in that animation from the Null School, very clearly shown on the oceans. Oceans are flat, right? There's nothing but water out there. So wind patterns get a lot more complicated wherever there are continents involved. Things like mountains can be barriers to wind. So these patterns, like the Hadley cells, are sort of global averages, but they don't mean that everywhere in the mid-latitudes, wind is only blowing in one direction all the time, right? Of course, there's variations on very small scales, and that's weather. So these patterns sort of are part of Earth's modern climate system, and small variations in these global scale patterns constitute daily weather. And so one of my favorite examples to think about this is to try to think about a river. Okay, so here's a video of some river rapids, right? And so what we see is that overall, this river is flowing, from the left side of the screen to the right side of the screen. And there are a couple of sort of big features that we can see here, right? There's sort of some standing waves right here, right? They're pretty consistently breaking. There's another sort of standing wave right here, pretty consistently breaking. Same thing over here, right? So there's larger patterns in this river. All the water is flowing downstream, right? It's all going from sort of left to right eventually. How it gets there is very, very widely varied. So you can see that on small scales, if you kind of wash over here, see these little splashes of water, right? There's small imperfections and perturbations in the overall flow of water downstream. So that's kind of like the difference between climate and weather and these sort of global scale wind patterns that we're talking about compared to daily weather. So daily weather, you can imagine, is basically these little splashes up here, right? Small, random, very unpredictable changes. And then the overall climate system is the river itself, right? Just generally air flowing in one direction. Now you might say to yourself, well, hold on a minute. Weather is predictable, right? I can watch the weather channel and they can tell me whether or not it's going to rain. So that's true, and it's because the weather systems move a little bit slower than this river, right? So it's very easy to predict weather, 1 to 5 days in the future, but trying to predict the weather 3 months in the future precisely is very challenging, right? You can imagine it might be very difficult to predict exactly how one of these little splashes is going to form, but if it was all moving much slower, right, you could see a splash starting to form, and you could say, now that I see it starting to form, I can predict where it's going to end up going. That's sort of like weather, and the sort of like 5-day forecasts that we're all familiar with, which are usually pretty accurate. So that's sort of my favorite example of trying to understand the difference between these large-scale climatic systems and daily weather. Daily weather are these little splashes, and the overall climate system is moving water, or in this case air, right, in our example, in consistent directions. But there's a lot of variation on small scales as to how that works. So these patterns of wind exist on Earth today, and they have for a very long time. For example, the wind caused by these Hadley cells in the northern hemisphere that generally blows sort of to the southwest here. These were the same winds that sailors participating in the slave trade found so favorable to take them from West Africa over to like the Caribbean. There in the Caribbean, they would sell slaves, buy things like rum and sugarcane, and then make their way up into North America, following these winds generated by those Ferrel cells, right? The Coriolis effect causing a deflection to the right in the northern hemisphere, regardless of the direction that you're moving. Okay, so these wind patterns have been around for at least hundreds of years, right? They were used during the slave trade between the 16th and 19th centuries, right? So 400 years, hundreds of years ago. But it turns out that these patterns of wind basically should have been active for as long as heat has been unevenly distributed across Earth's surface, which is to say, as long as Earth has been a circle or sphere, right? Which is to say, forever. So to illustrate this idea, here is a paleogeographic map of the Earth's surface some 300 million years ago. So MA stands for Mega Annum. This is a reconstruction of the supercontinent Pangaea. An enormous amount of geologic information is incorporated into these paleogeographic reconstructions. And what you can see is that in these very same bands of sort of 30 degrees north and 30 degrees south, Pangaea is depicted as having these extensive deserts. And this is supported by many lines of geologic evidence. So for instance, the rocks, so if you can kind of recognize the west coast of South America here, this is basically South America and Africa. You can sort of see Africa is like this. Here's the Horn of Africa, right? So the central part of Africa, which is today lush jungle, was at the time, about 300 million years ago, arid desert that looked much like the Sahara Desert of North Africa today, right? Giant sand dunes, very, very dry, very, very hot. In fact, one of these lines of geologic evidence is that these sand dunes in this part of Pangaea actually record wind directions that make sense with what the trade winds would have looked like. So the trade winds would have probably been blowing in this sort of a direction, and in this sort of a direction. And so in these giant Pangaean deserts, the dunes actually record wind directions. So dunes are moved around by wind. And the ancient sand dunes of Pangaea actually record these wind directions that are completely consistent with the trade winds. So the trade winds caused by Hadley cells have sort of been around for at least 300 million years. They've been around for as long as the Earth has been a sphere. So these same principles, basically just driven by the uneven distribution of heat on the surface of the Earth, the fact that hot air rises and cold air sinks, right? These basic principles have been driving Earth's weather systems for, all of Earth's history. So some things about the Earth's climate remain constant, but many things about it also change. So as we move throughout the rest of this section of the class, we'll be trying to understand some of the ways that Earth's climate has changed through time, what things cause those changes to happen, what things remain constant about Earth's climate through time, right? We're going to try to learn all these different things in the next couple of weeks.